states, you emit a photon. So that's the picture that he gives, and the evaporation is just a slow descent to the states, like an atom, you slowly cascade down, and it slowly comes away. So it's very simple. It all follows from what everybody knows and loves about physics, about quantum mechanics, and about string theory. Okay, there seems to be a plausible argument. Now, if you ask, of course, at the end of the day, if you actually look at these solutions you get, say from far away, obviously far away, even these naked microstates do look Schwarzschild like. You have a mass, and far away, we know that everything looks like a black hole anyways, or looks like a point mass, doesn't really matter what it was, Newton knew that already. So any deviation from far away presumably will drop off as a multipole. So the higher order multipoles will be weak far away. And so what you want is you want a precision measurement of your space-time somehow at a radius not too large. Okay, large enough that it's really some higher multiple of this that you want to see if there's any trace of the deviation of the system from being a Schwarzschild black hole. Let me just give a bit of just I'm misusing the word landscape. It means other things in this field, but I just want to give you the background of when I say this fuzzball is certainly not the only view in town by any means. Probably a more fashionable one these days, as a firewall picture. Again, it gets around it by not allowing you to look inside. And there are other ways of getting rid of it. There used to be a time when people talk about remnants. There are many. Obviously, this is an old problem, and there are many proposed directions people have thought about. And in most cases, this has been hampered by what I started with. The fact that this system seems to have nothing to do with anything in our universe, so how will you ever know? Okay, if none of these things exist, and none of these effects exist, people say that 1,000 years ago, scholars were debating how many angels can dance on a needle. It seems a little bit like that. You're asking a question that you will never know. This is just, an aesthetic debate based on some bizarre assumptions. So, can we just, again, think a bit harder? Is there something we could actually measure? And what would it take? Okay, what would it take? And what might the outcome be? And it's only when you actually think of a more concrete measurement that you might understand a bit more of what gravity and quantum mechanics is, or is not. So, gravitational lenses. And of course, there are people here who are more expert on this than I am, but it suffices to say that you all know that a gravity bends light. Einstein knew that. And near a black hole, I think things in the background look distorted, but more importantly, is if you have a point source behind the black hole, you will see multiple images. In the simplest case, you will see two. Lots of again, I'm simplifying life a huge amount, you see. I'm trying to make this easy, and somebody may tell me, there's an infinite number of images, that's true. But for this purpose, there are two images of any object in the background near a black hole. It turns out this infinite number of images get exponentially fainter. They're actually quite hard they don't really matter. So for all that matters, if I put the object somewhere behind, I get, in particular, I'm thinking, of course, about pulsars. We already have a pulsar behind this, near this black hole. So right now, depending, of course, whether the black hole is, well, I don't know, hopefully the black hole is a bit behind the black hole, at least it will be after, if you wait for 100 years. And then you will see where the pulsar is, and on the other side of the black hole, you will see a fainter image of the same pulsar. And because gravity is strong, well, even if it was in front of the black hole, of course, sounds like that can go back, wrap around 180 degrees, and you will still see an image, but that image is very faint. So what you want is a nicely aligned, you want the black hole to be, the source to be nice, straight behind the black hole, to see two images. That's, I think, the system we want to have in mind to ask the question, what might you see? So I'm going to, and since we don't actually know all that much about this black hole, this one I think it's more like 100,000 Schwarzschild radii, but again, none of that is important. I mean, it is important, but I'm just going to make some numbers up to go through what kind of experiment you might think about. Okay. Imagine a pulsar orbiting a black hole at 10,000 Schwarzschild radii. That's a number that's, well, first of all, not too far off from the black hole with the pulsar that we have measured. It's probably 1 more 0, but whatever, what's a 0 for this argument. If it's a solar mass black hole, that's about the smallest it can get without it evaporating by gravitational radiation in a short amount of time. So it's hard to make it much smaller, even though, of course, the smaller the better, but it's unlikely you will find a smaller companion. You want an inclination that might be a square root of that, okay? Because if you incline to within a percent, then you get a order unity strong lensing when the pulsar passes behind the black hole. Okay? Otherwise, if it just flattens the plane, obviously it's not much of an effect. You want it to go behind. And then what we're going to do is we'll take the pulsar and we will see 2 images in this simplest world. And these 2 images now form a double slit interferometer. Young's double slit experiment. You see 2 beams of light. And it doesn't even matter whether you resolve those 2 beams, because those 2 beams will interfere. You get constructive and destructive interference. The phase change will be of order a few centimeters, like this, which for pulsar radiation is an order unity effect. Okay? So what it means is that normally pulsars should scintillate perfectly if it stayed coherent, so in a Schwarzschild metric. And you can calculate exactly what would happen because space-time is static. This really is a double slit pattern, and you really get full modulation. Pulsar scintillation is described by modulation index, and you will see the pulse flux go to 0, and then to twice that, and then to 0 again as the pulsar moves across the slit. Now, if, however, the lens is not a Schwarzschild black hole, okay, if instead it is a fuzzball or a quantum mechanical object, well, then your lens is quantum. And then what happens, what the way you're supposed to do the picture is you take your incoming photons, 1 photon at a time, that's how double slit experiments work, 1 particle at a time, propagate each particle through the lens, some amplitude and square. Okay, that's the way that we do quantum mechanical double slit experiments. Now, of course, these microstates are not eigenstates of photon propagation, so each photon will actually go through some different permutations of eigenstates, meaning that in a general incoherent quantum lens, the interference pattern will go away. Okay, that's the generic outcome of a quantum lens whose eigenstates don't commute with the photon propagation. So, in such an experiment, you would expect to see effects of potential quantum mechanical fluctuations due to the Hawking. In Maser's picture, it would be due to the Hawking photons interacting with the space-time. And note that these wavelengths are not that far off. The Hawking radiation, even though it is somewhat longer than the pulsar radiation, they're both in the wave optics regime and are treated by the same physical effects. We're no longer trying to have these gigantic discrepancies in scale. Yeah, so this is now a concrete picture. I can ask, instead of having some vague notion, maybe it's a firewall, maybe it's non-local, maybe it's something else. Well, no, we can now put each of these pictures to on the bench and ask. Okay, let's calculate, let's measure, let's see what is or isn't happening, and use that as an inference. You may find that there is no quantum mechanics in gravity, or whatever that can be. Not to say that this has to happen, but at least it's something which could happen. Right now, there are, the last time I checked, which was a few months ago, there were 11 pulsar neutron star binaries. As of today, there is one pulsar black hole binary known. Okay, that's our total inventory. It's thought that new surveys, in the background I'm showing a picture of a new survey telescope under construction in Canada. It's meant to do 21 centimeter work, but it's a very convenient wavelengths for pulsars. In fact, almost all pulsars known were discovered by 21 centimeter instruments because they share the same wavelengths. It's a low frequency phenomenon. And this will have a survey speed about 1,000 times faster than any telescope right now. And obviously this is just the first. We could imagine many more of these telescopes. But even this will substantially increase the population. If you build one in the southern hemisphere, it'll make an even bigger impact because that's where the galaxy sits, galactic center sits. And of course, in the further future, there are instruments like the square kilometer array that will substantially increase, and we should have hundreds of pulsar neutron star binaries and presumably a number of neutron star black hole systems. And if we're lucky, there'll be one at the right inclination for us to actually think about what this experiment will give. So this is the basic direction that this field might go to. Well, this actually brings me to the end of this argument about the question I was trying to provoke is, can there be astrophysical tests of quantum gravity? And what I'm saying is, what you want to look for is, I may have used the wrong word, since I don't know, I should not astronomy that well. I don't know if high inclination means you're almost edge on. Can anybody correct me? Which way is high? I don't know, whatever, you need you need to be edge on, I don't know if it's high or low. Inclination binary. I think there are technologies that have a lot of potential. If one thought this was interesting, those telescopes are very cheap. This chime is on the telescope scale, it's a $10 million telescope. One could build something much bigger than chime. Could build something 10 times bigger, 100 times bigger than chime at a budget that's not that high. And I think this is at the very least, a system where you can ask, even without such a system, even without having a binary which is the right inclination and the right candidate, at least now we have an example of something which could have been, and about the questions we can ask. Okay? We can ask, is there, do we have a hope of seeing traces of quantum gravity in data in the foreseeable and hopefully not too far future? Thank you.
Questions? Exciting idea. How do you get this large number of degenerate microscopic state, this G1?
So in the first broad picture, I mean, again, I'm not actually an expert on any of these. This is Samir Martha's picture. So when you say how do you get that many, it's I think it's a little bit, the devil is in the details, because we're asking what did I really mean by each of these statements, and this is just a order of magnitude argument he gives as to why the Boltzmann equilibrium can be very far off. Okay. In his picture, well, if you actually count how many microstates can correspond to a given macrostate, that's the G you should be putting in. it turns out, of course, that it's not as if for any astrophysical black hole, anybody could write down all 1077 states to, for you to search through. So there's nobody who has a useful computation that's it's not even unlikely you will ever have a useful quantitative description, but it is an estimate, right? That's the number of microstates that has to go in to explain the entropy, and it does go in certain special configurations that Marsler and company do construct. So if you the way they construct things is you wind strings.
It's related to a surface area.
In the simplified view, yes, you would just say that that entropy is related to surface area, and they have a number of states goes actually exponential of that, and that's just a huge number. So just to say the font is a big bit of the inside.
Do you expect it will be related to the age of the black hole?
So that's where these pictures differ a lot from each other. In the fuzzball picture, no. Fuzzball pictures, black holes always have the entropy independent of age. And there are microstates, and the macrostate is what you say when you don't know the microstate. Okay, that's just the simple classical description. And the thing you have to let go is that, but each microstate is not a Schwarzschild and has no horizon. Now, in some of the alternatives, like in the firewall picture, people point out that this information paradox isn't really verifiable until the black hole is what's called old. It's called a page time. So after you lose something like half your mass, that's when the entropy that has come out is bigger than the entropy inside the black hole, and then you've got a real problem. Okay, so they might say, well, how do you know there's a problem? I mean, there are many things that you don't know, right? So when I say one photon comes out, for me to know that there was a problem, I would have to look inside to know that entropy has gone up. Entropy, just by only seeing half a system, might appear high, even though it's not. And but of course, after half is going to come out, I've got more entropy out there than I have inside, and that's what they call an old black hole when that happens. But no, in this picture, there's no age dependence.
In the double slit experiment using the pulsar light, it seems to me you only need classical gravity. So
only need
classical gravity.
Classical gravity. Normally, yes.
So in what sense is the test of quantum gravity?
Oh, in classical gravity, in a double slit, you get perfect what's called modulation. Okay, so if it's purely geometric, then the flux will go to exactly 0 at the null of the interference and go to twice at the peak. If you have a quantum mechanical lens, okay, my lens was a superposition of different geometries, then I might see no modulation at all. And of course, that's why they give big numbers such that the fluctuations are comparable. And because the double slit is very, very sensitive, you're sensitive to very small deviations, and that allows you to test even at multiple, with doing a test at 100 Schwarzschild radii. It's fairly far out. I'm just trying to look for tiny changes in that radius.
So if gravitational wave gets detected, can we use the information from gravitational waves to discern the various pictures?
Gravitational waves, that's Samir Martha, I did ask him that question, and he said probably not. Okay, so again, these things are obviously hard to view all aspects. I think the important picture is that what you see depends on exactly on how you go about measuring it. So the example he gives is the system where you probably don't see any difference is if you have let's say a star or a neutron star, if it's an orbit around a black hole, okay, then even though the black hole is a superposition of non-Schwarzschild objects, if you have a classical test object, in this case, 10 to the 50 atoms strongly interacting with each other, and those orbit a system, then unlike in the photons don't talk to each other. They all go through individually. In the case of a star, the atoms collide with each other, much more quickly than they collide, than they interact with gravity. So what they feel is mostly the collision to the neighbor. In that case, even though it is true that each atom may instantaneously see a different space-time, but once you average over all the atoms, okay, in these black stringy constructions, the expectation space-time is Schwarzschild. So when you take a macroscopic body orbiting a black hole, even all the way to the innermost stable, circular orbit and inside, you would see the classical space-time. That's in the fuzzball picture. Okay, so everything looks completely classical. If you were to build a spaceship and you go around, and that was your measurement, that was your device, you would see no deviations down to the number of particles you have from a Schwarzschild metric. So it has to be a coherent interference experiment, like photons passing. So for lensing, you get a different answer than you do for a satellite orbiting it. I think that's important. That's a very important aspect of these pictures. That how you measure it may determine what you see.
So you mentioned about the multiple component. Is there any estimate on the, say, the amplitude or the spectrum of the multiple composition? And how about a curved black hole which is rotating strongly?
Again, just the caveat, I'm not an expert in actually any of these. These are lensing, no pulsars, no fuzzballs. But yeah, and first of all, also my distant understanding is that they can reproduce many of the limits of real black holes, but in fact, the ones that they can actually do calculations of are black holes that are close to extremal charge. So that's where the calculation gets easier. So not only the black holes that have been for which these models have been built are not actually Schwarzschild black holes that we're talking about. Okay, so and then you extrapolate saying, well, it's close to extremal charge. Now, of course, in principle, the arguments should hold for rotating. So in principle, yes, all of these are allowed. In practice, the calculation gets tough. When you're rotating, you've got one less axis of symmetry, hard to calculate things. But yeah, in principle, it's meant to hold for all of these. And yet, one more question, I thought. No.
Spectrum of multiple.
Oh, the multiple spectrum. Now, again, Marso constructs a two-state black hole. Just to go through what you do in order to just get entropies. In string theory, what you do is you say you have an internal dimension, which is, let's say, compact. Let's say it's a circle. You take a string, and you can take a string and wind it like a rubber band. You can wind it twice, 3 times, 4 times, 10 to the 77 times. You would be sitting here forever. Not forever, 10 to 77 seconds. And then you have 10 to the 77 black charges. And from far away, this looks like a solar mass black hole. Okay, that's how you make. That's one way of getting a lot of mass by just winding your string and sitting for a long time, or whatever, winding it up. Another way you can get the same energy is just wind your string around once, and then I excite it, so it can vibrate. I can have a first excited state, second excited state. I can keep exciting it, and if I were to excite it 10 to the 77 times, I would have a solar mass of excitation energy in the same string at the same place. From far away, because all I can measure is total energy, those two look the same. Entropy comes because you say, well, I didn't actually know if all I tell you is the mass, then it can be some combination of how many times I wound it and how many times I excited it. And that's the entropy thing I don't know. Okay. So what Samir does is he says, okay, for the zero entropy case, when it's only wound, I can calculate some space-time. In the case when you're only excited, I can calculate some space-time. And in between, who knows, right? So that's, yeah.
What about a black hole that is actively accreting mass?
A black hole that is actively accreting mass. Again, in an accretion disk, I think Samir's argument would say you have atoms that probably strongly interact with each other much more strongly than they interact with the black hole itself. And again, there are all the practical questions. It's actually very difficult to precisely compute what an accretion flow does with plasma physics. So there you have the challenge that both, it's difficult to, unlike a neutron, a pulsar going on is just Newtonian or whatever. It's a simple calculation to calculate that, whereas for an accretion flow, it would be more challenging to come up with a clean prediction. And I think the general prediction would still be that even if you could do it, the strong interaction of those atoms with each other likely makes them see a Schwarzschild spacetime.
Because your experiment, in this observation, you're trying to see the coherence of the interference pattern. Then if you don't actually, if it turns out that you don't see any interference pattern, how do you know this is because it is due to the decoherence, or there is no quantum effects at all?
Okay, let's see. So let's say we do the experiment, and there are two possible outcomes. Either I see the interference, or I don't.
Yes.
Okay. If I don't see the interference, so in general relativity, if there's no quantum mechanics, I mean no quantum mechanics, I mean no quantum gravity. Okay. In no quantum gravity, now just be a bit careful of what we're saying here. We're saying that there's no quantum gravity, but there is quantum mechanics for my photons testing it. Then I do see interference. Okay, double slit, like in the case of our sun, actually people have gravitational lenses, and here's the you can talk. There's an expert right here that we do see objects behind lenses for which we see multiple images. Okay, such systems have been discovered, and that's known to happen. But typically they don't interfere with each other because the source is too large to actually scintillate. But quantum mechanics, or at least classical mechanics, we know does hold for these geodesics. So I would say seeing it scintillate shows that there's not a quantum gravity interaction, and that semi-classical does work without any back reaction. Now, and then you would say, well, okay, so you've got to find some other resolution to Hawking's paradox. So this non-local, this local one that Samir proposes, would then fail the test. If you don't see an interference pattern, okay, then, well, there are two basic possibilities. Number one, you might say, well, there's something wrong with just classical GR, because that predicts you would see it. Classical GR plus wave plus geometric optics, or semi-geometric optics, you would see it, and you don't see it. That'd be more interesting. And of course, then you have to convince someone that this really is due to space-time and quantum mechanics, and not due to black hole. I mean, it turns out that in these binary neutron stars that we do see, when they occult each other, sometimes there are other plasma effects which may affect your scintillation. So one does need obviously more work to establish it to be real, but that would be the exciting one.
All right, sounds like a good point to stop. If there are no more questions, let's thank the speaker again.